I'm going to carry on talking about methods for computational inference, but this time around I'm going to switch track entirely. And so the good news is, if you've not really followed the previous two talks, you can forget about it, all of that now, and you won't really suffer for it in this one, because I'm no longer going to be looking at reverse time coalescent systems with or without recombination. I'm going to be talking exclusively about inference for diffusions. So I'm imagining observing allele frequencies forward in time in a population, and I want to use a diffusion model to understand what information that carries about the dynamics driving the evolution of the process. The methodology, however, will still be pretty much similar. So I will start by introducing a particular instance of the Metropolis-Hastings algorithm called the Gibbs sampler, and that's the tool I'm going to be using in order to sample from these distributions that I'm interested in. And the kind of moral that can be similar, I'm going to end up using a sample from a target distribution as a proxy for the true density of the distribution, if you will, so that I can look at distributions of quantities of interest. And diffusions have this awkward property of having infinite dimensional realizations. And there's nothing a computer can do about the fact that it cannot store an infinite number of numbers. So necessarily I'm going to have to do some sort of discretization, and the bulk of this talk will actually be about how you do that discretization in such a way that it creates no error whatsoever in your target distribution. So I'm not going to allow myself the luxury of putting in just a simple fixed time discretization grid and taking on a little bit of bias in the form that I'm using an Euler-Maruyama approximation of my diffusion or something like that. I want to be able to do this exactly, and quite amazingly that turns out to be possible. Towards the end there are also sort of two sections on more heuristic methods. I may or may not get to those, but they're in the slide pack anyway. If anyone's interested, you can have a look afterwards, and we might even talk about them if I keep a healthy enough pace. I'm going to go through the main program of this sort of so-called exact simulation methodology twice. First, for models which look like Brownian motion. That's just an easier case that I'll go over first. And then I will talk about how to specialize to the Wright-Fisher diffusion, which turns out to be a bit more intricate, just because the diffusion coefficient in particular is more complicated. All right, this is the Gibbs sampling algorithm, and again, nothing about diffusion paths yet. I'm imagining I have just two variables that I'm interested in sampling. They have some joint distribution, which I'm denoting by pi, and I want to create samples with Metropolis-Hastings. And, well, this was the Metropolis-Hastings algorithm that's already appeared in both of the previous talks. I sample an update from some proposal distribution, and then with a probability which depends on both my target distribution and my proposal distribution, I either accept or reject this update. And this probability has been tuned in exactly such a way that pi is a stationary distribution of my chain, and so I get samples from the distribution which I want to evaluate. Now I'm going to choose a very particular q. So I want q to be in the first variable just a delta mass, so I'm not going to change one variable at all. And the second one is going to be updated using the true conditional distribution of my pi. What happens with that choice to my acceptance probability? Well, I just do a little bit of substitution in algebra, and I realize everything cancels. I get an acceptance probability of 1. So I have an instance of the Metropolis-Hastings algorithm in which I have to be able to sample directly from the conditional distribution, but if I can do that, then I never actually need to evaluate my acceptance probability, because I know it's identically equal to 1. Yeah, this carries the name of the Gibbs sampler, and is by now a rather old algorithm as well, and has found applications in myriad areas. It's sometimes more efficient than a general Metropolis-Hastings algorithm, sometimes less efficient. There's sort of no clear preference between the two, except in particular contexts. But for this diffusion problem, this turns out to be the convenient setting. So here's a kind of more specific summary of what the Gibbs sampler does. I have this bivariate chain with joint distribution pi. I start from some initialization from arbitrary initial conditions, and then I iterate these dynamics where I sample a perturbed first variable using the conditional distribution. So this is my second variable at my I-1th step. And then I don't need to do accept reject because I know it's going to be accepted. I just record this variable, use it in the second conditioning step, record the second variable, and this is my next state. And then I iterate. But yeah, frequently sampling from this conditional distribution can itself be complicated. So I know I can't directly sample from the joint distribution pi. If I could do that, then I would never bother doing this in the first instance. But I'm saying I have to be able to sample from this guy. Well, sometimes that's possible. Often it's actually also somewhat difficult, but there is also a relaxation you can make, which is you can, instead of just executing this thing in one line, you can at this step run a Metropolis-Hastings algorithm targeting this conditional distribution, and here run a Metropolis-Hastings algorithm targeting this conditional distribution, and that still turns out to be a valid algorithm. What's the advantage? Well, these things are typically, of course, lower dimensional than the full state, so it can be advantageous even then to run several kind of inner Metropolis loops rather than just one global Metropolis-Hastings chain. Again, which is the better idea in general is not a well-posed question. Okay, so here's a discretely observed diffusion model. I'm going to suppose that I have some stochastic process. All of my diffusions for this talk are going to be scalar. In some cases, what I'm going to talk about can be updated to many dimensions, but it gets much more restrictive. So scalar will be enough. I have a diffusion model dxt, which is governed by some drift, which has an unknown parameter theta, and a unit diffusion coefficient. Unit diffusion coefficient is important for reasons which will become clear in a couple of slides. Essentially, I need the law of this guy to be equivalent to Brownian motion. I could relax this somewhat by remembering that in one dimension I have a tool called the Lamberti transform, which lets me take a diffusion with a more general diffusion coefficient and map it to a diffusion with a unit diffusion coefficient. But the crucial thing is that even then the diffusion coefficient can't depend on these unknown parameters. So this is really a rather good cartoon to keep in mind of what it is that I'm allowing myself to do. I don't know how comfortable people are in the audience with diffusions. I'm assuming most people are very comfortable, but in case there is someone to whom this is moderately mysterious, well, all it is if I didn't have this guy here at all, and I could divide through by dt, I would have a time derivative on the left-hand side and a force c term on the right-hand side, so I would have an ODE, and the ODE would describe the kind of mean trajectory of these. This wiggly thing is a realization of a random path, and its mean would be described by the ordinary differential equation. And this thing, well, it just adds the random noise, the kind of very small jagged fluctuations you see around the path. And that's really a good enough grasp of diffusions already that the rest of my talk on a high level should be at least somewhat accessible. So what am I actually doing to this diffusion? Well, all of these dotted lines are supposed to be observation time points. So I'm supposing at these 1, 2, 3, 4 times, I get to observe the state of my diffusion, but I don't see the rest of the path. So you can imagine, for instance, having time series data in genetics, where maybe you have data from the present day population, and you've also got some archaeological or other kind of historical data that gives you partial information about what the allele frequencies were like some time ago in the past. That's the sort of setting that I'm imagining here. I'm purposefully vague about whether I observe the state of my diffusion precisely, whether I get the exact true state of the diffusion or whether there's some observation noise involved. So it could be that I observe actually a binomial random variable with this success probability or something like that. That will all get encoded into this, which is again a likelihood function. And now my likelihood depends on the unknown parameter, and there are these. X will be the state of the underlying diffusion. I'm assuming I've given myself the initial condition as well, just for simplicity. That's not strictly necessary, but makes life easier. Y's are the observed values, And this likelihood, again, same way as in the coalescent, is only available as this sort of high-dimensional integral. I am integrating over the transition density of my diffusion. Delta is my time separation between these observations. And yeah, this is going from the previous observation to the next observation given the parameters. And this G here is supposed to describe this possible observation noise that I have in mind. So if I observe one of these binomial random variables, for instance, with success probability given by the state of the diffusion, then this would just be a binomial mass function evaluated at the observed realization that I in fact saw. And these integrals are with respect to the kind of underlying path in the case where I'm not observing my time points exactly, or I have observation noise. These are integrating over the true underlying state, which may be unknown. For simplicity, for the rest of the talk, I'm in fact going to assume that these G's are delta masses at the true state of the diffusion, so that corresponds to me observing the diffusion exactly. But that's not really with loss of generality, because if there is observation noise, then probably the first trick I'm going to do anyway is use my favorite data augmentation scheme and condition on the true underlying state of the diffusion and think of those as extra static parameters. So I'm going to allow myself to observe the diffusion exactly at these observation times, but that's not really in practice it's not a conceptual change in any way, and that gets rid of these integrals from this picture. But then I'm still in a mess, because for virtually any diffusion of interest, I don't know this transition density. So I have a likelihood, it's not got any integrals now, but I still can't evaluate it. So now I'm going to make my situation seemingly much, much worse by doing another data augmentation layer and reintroducing integrals. And I've now changed notation slightly. This is not the transition density anymore. This is the actual measure on, say, Wiener space or whatever space of continuous functions you like, which describes the law of the diffusion paths themselves. So I'm sort of data augmenting on the whole infinite dimensional path of the diffusion. This is my notation for a bridge. It goes from xi minus 1 delta to xi delta in time delta. And I'm still assuming that I'm observing the state of the diffusion at these observation times exactly. And these integrals have reappeared because I'm now integrating over everything else that happened in the meantime. So this is integrating over the whole diffusion trajectory, conditioned on hitting exactly the observed positions at the observation times. And this is the law that I'm going to be working with. This is a somewhat horrible slide. I'm going to go through it rather gradually, and we'll get through eventually. There are going to be a few like it throughout the talk, for which I apologize. I could not come up with a nice way to summarize this on a slide. So I'm kind of, whatever it is that I'm going to do henceforth, somehow I'm going to have to contend with the fact that I have to be able to handle this kind of bridge measure for my target diffusion. And I'm going to make a start by writing this as a Radon-Nikodym derivative against Brownian motion, against the Brownian bridge. The reason for that is that I at least know how to simulate Brownian bridges. The Brownian motion has tractable transition densities, it has tractable bridge densities, it has tractable pretty much anything. So if I can reformulate my problem in terms of something tractable like that, then that sounds promising. So let's do that. That's what happens here. This is just the Radon-Nikodym derivative between the bridge measure I'm interested in and the law of a Brownian bridge. And yeah, law of a Brownian bridge appears again. The next couple of lines are just notation. So capital F is the integral, the definite integral of my drift coefficient. And then this thing turns out to be really the star of the show, this function phi, which is 1/2 drift squared plus the first derivative of the drift. That turns out to be the quantity that I need to be able to work with in order to make progress with my exact simulation framework. And the first assumption that I need to make is that this thing is bounded below by some finite constant, uniformly in the state of the diffusion. If that is the case, then I can write my Radon-Nikodym derivative in a nicer form. So this is a factor which depends on just the transition density of the Brownian motion and the true diffusion that I'm interested in. These are not bridge densities, these are just the transition densities of the processes. And then I have an exponential of these sorts of integral terms, and then an integral over this function phi. This comes out of essentially a two-step calculation. The first thing is you write down the usual Girsanov formula for this Radon-Nikodym derivative. And then the second step is you hit this function capital F with Ito's formula, and the result turns out to be something which you can exactly substitute into the Girsanov transform to get rid of the stochastic integral, and what remains is this guy. Now over here, remember that I'm observing my start point little x and my end point little y exactly. And so let me check what here actually depends on things which are variable. Well, this only depends on the endpoints, so that's effectively a constant for any path that I'm going to be plugging into here. So from a simulation point of view, that can get absorbed into a normalizing constant. Likewise, the capital F's don't make any difference. Let's put those into a normalizing constant. And then I want to introduce my lower bound in. So that's where this comes from. The only thing which kind of depends on the state of the diffusion is in here. And this now, by definition of phi minus, is less than or equal to 1. So I can interpret it as a rejection probability or an acceptance probability. That's where we're going to be going with this. So if I pretend for a moment that I have access to a computer which can handle infinite dimensional objects, can sample diffusion paths in their full glory, then I can do the following. I can sample a Brownian bridge from the law of the Brownian bridge with desired start point, end point, and time increment, and sample a uniform random variable. If the uniform random variable is small enough, which is to say less than or equal to this thing that I said I wanted to interpret as an acceptance probability on the previous slide, then I accept this path. Otherwise, I try again. This would give me realizations exactly from this density here, this bridge measure. And so that would be a very useful step toward having access to this sort of Gibbs sampler, where I'm iterating in one update. I'm updating the diffusion bridges, all of them one by one using this sort of algorithm, and then the other update would be keep the bridges fixed and update the static parameters. I haven't talked about that part yet, but we'll come to it. So that would be the way to go if we had access to this sort of machine, but we don't. So what can we do? Well, here's an almost practical tweak on that that previous slide. In fact, if I flick over to the previous slide, the important thing is not to actually evaluate this probability. We don't. But rather, all we need to do, all that's important in this line is we have to be able to simulate an event of this probability. I don't strictly need to know what that probability is, as long as I can guarantee that whatever event I've simulated is a Bernoulli random variable with that probability. And again, bizarrely enough, sampling an event can sometimes be easier than evaluating the underlying law, and this turns out to be another example of such a time. So I'm going to be constructing in a finite dimensional way an event which has exactly this probability, and that gets me around having to evaluate this sort of path integral over a diffusion path. So here's an almost practical way to do this. Instead of I'm still going to flick back to the previous slide actually, because yeah, what's going to be my event? Well, this you can recognize as a probability of a Poisson process of intensity phi theta minus having 0 points in this region, in this region of time. So Poisson realizations of Poisson processes, unlike diffusions, are finite dimensional almost surely, as long as there's no infinite intensity component, which there isn't here by assumption. And that's what's going to enable me to make progress. And that's finally, now let's try for a third time to go into this slide. That's what these points are going to be. I want to simulate time points and space points from a Poisson point process with this inhomogeneous intensity given by this, the exponent on that previous slide, in this window of time that my bridge is covering. For each of these points, I'm also going to need to create the corresponding state of the diffusion bridge. And so these are going to be points sampled from the Brownian bridge. And now I have to make a comparison between my Poisson points and my Brownian points. If there exists one of these times where I have a Poisson event where the corresponding Brownian motion is at a level which is below the level given by the Poisson point process, then I have to reject my path. If this doesn't happen, if all the Brownian points lie above my Poisson points, then I accept. And when I accept, I return this sort of finite dimensional cloud of points. These Poisson components, the first two I'm going to be referring to as skeleton points, just for terminology, and these are just the states of the Brownian bridge. And this gives me an accept-reject mechanism, and if you stare at it for long enough, you can convince yourselves that this gives me exactly this probability. So the probability that there are no Poisson points underneath the graph of the diffusion path. And of course, to make that determination, I don't need to know the whole diffusion path. I only need to know the diffusion path, exactly the points where there is a Poisson point. And that's what lets me project down to this sort of finite dimensional thing, which I can actually store and manipulate on a computer.
Sorry, I'm a bit confused. I mean, because you use somehow a pointwise rejection rule, while this looks a bit like an integral type of...
Yes, so maybe I'll draw a picture of this. Here we are. So suppose that's my time window. So this is time delta, this is time 0. And I have some realization of my diffusion path. And I'm thinking, do I want to accept or reject this path? And a priori, it depends on the whole path through this integral in the exponent, exactly as you say. But by recognizing that as this kind of 0-point probability of an inhomogeneous Poisson process, I can then layer on a Poisson point cloud on this image. So maybe there's a Poisson point here, and a Poisson point here, and a Poisson point here, and a Poisson point here. That's the realization of the Poisson point process. And now the question is, well, what does this correspond to? And here we have points underneath the Brownian motion, which is a kind of violation of this condition. There are more than 0 points, and so the event of this probability has not happened, and therefore I throw away the whole path. But of course, in order to make this determination, I don't actually have to know the whole path. It's enough for me to know the state of the path at this time, at this time, at this time, and at this time, and that will allow me to make this random decision without knowing the whole path. And so all I do is I invert my order of simulation. So I redraw the same picture, but this time I simulate the Poisson points first. Let me put them in the same places, more or less. And then I ask, well, I'm simulating a bridge, right? So I also know the initial point of my diffusion path. So then I say, well, where is the diffusion at this time? And I just simulate that realization, it's over here. And then at this next time, it's over there. And then here, and then here. And from just this realization, I can make my decision as well. And now there's no need to know the whole path. I never actually need to evaluate this integral.
So how many points do you need to sample to make this happen?
However many your realization of the Poisson point process happens to spit out. So fewer points tends to be better from a performance point of view, which corresponds to essentially this Radon-Nikodym derivative being closer and closer to the identity. So the closer you can make the law of the path you're actually simulating and the target path, the better off you are. But yeah, it's not a fixed number; it's random in itself. And importantly, this sort of skeleton of points will be enough for me to do the update of any static parameter as well. So it will be a rich enough projection of my diffusion path that I can make a correct update in a second step of a Gibbs sampler of my static parameters given the path. And therefore, I'm going to be able to iterate this kind of logic of update path given parameters, update parameters given path, path given parameters, parameters given path, and my chain is going to be able to mix over the whole space that I'm interested in, and I'm going to be able to do proper Monte Carlo. Okay. So there's a further nice feature of this sort of construction, which is suppose I'm actually specifically interested in my path at a particular time. Try to be fancy and use a color. So maybe I not only want to do this sort of inference process, but I want to know the state of my path in the middle. So there's a particular time, and my quantity of interest in my inference is what was the state of the diffusion at this time. Well, once I've done this accept reject step, I can then fill in further time points from my diffusion process by making use only of this proposal mechanism. This path has already been accepted by my process, and ostensibly the acceptance charged the whole infinite dimensional diffusion trajectory, and so this whole object has been accepted even though I haven't yet simulated it. And so if I want more detail, more time points, I can just fill them in with no further rejection control, and it turns out they are coming from exactly the correct distribution. So this is, I think, the amazing thing that you really can, in a way, push the whole of this infinite dimensional integral into a random finite dimensional object without any loss of information. Okay, so I say this is almost practical. Why is that? Well, in practice, simulating an inhomogeneous Poisson process is still very hard. I can draw it on the board easily, but that's not really sufficient. I have to be able to create this point cloud in order to employ this mechanism. And that's straightforward, provided that I make a further regularity type assumption, which is I not only want this phi to be bounded below, I also want it to be bounded above. And as soon as it's bounded above, well, then my life is pretty easy, because now I just simulate a Poisson process with this maximal intensity, and then I do Poisson thinning. So I simulate my point cloud from this upper bounding Poisson point process, then I do some thinning to it, and then only on the thinned points do I check my rejection control for my diffusion process. And if my path gets accepted, then I only need to return the thinned points, not the ones which got thrown out by Poisson thinning. And this now is really an algorithm that is implementable on a computer nicely. It's legitimate to ask how often are these bounds satisfied. This one fairly often, this one not so often actually. But there are more sophisticated tricks you can do to get around this upper bound. Essentially, these tricks, which I won't go into in detail, but they will consist of, first of all, simulating a global upper bound, a random upper bound for your diffusion path, and then you have to promise to do the rest of your bridge simulation conditionally on not exceeding that level. And that will give you a kind of random realization of this upper bound for a given iteration of your algorithm. That's how you can relax these sort of boundedness requirements. So they're not so harsh in practice as they appear. Okay. So this is just to sort of summarize the full Gibbs sampling algorithm. I initialize some static parameters as well as this kind of point cloud of Poisson points and diffusion points, again from some arbitrary initial condition. And then I iterate the following. So first of all, I keep my static parameters fixed and I update my Poisson points and my diffusion points using this exact algorithm that I've just sketched out for you. And then in a second step, I want to sample the static parameters given all of these points that I've simulated. This is typically not a conditional density that I can write down in a nice normalized closed form. And so here I have to resort to actually running a Metropolis-Hastings algorithm targeting this conditional distribution. But as long as I can write down this conditional distribution up to a normalizing constant, then I already know how to do that because we've seen it in previous talks. What does this conditional distribution look like? Well, it's proportional to the joint distribution, which is itself proportional to this factor is just a prior distribution on pi, the static parameter. So you're well within your rights to ignore it if you prefer not to be Bayesian. And then you have the same sort of exponential factor of these antiderivatives. And well, a bunch of other factors which have to do with the kind of, for instance, you can recognize contributions from a Poisson process of the upper bounding intensity. Here you see the sort of Poisson thinning terms. These are contributions from the underlying Brownian bridge rather than the bridges from the diffusion process I'm actually targeting. It's a bit of a mess, but all of these factors that appear in this are explicit, they're tractable. I know how to evaluate those things. There's nothing in there which is an unknown transition density of a diffusion or something like that that I have to sort of work hard in order to get a formula for. And so I can just make myself a particularly large coffee and write this up in C or Python or whatever you like. And it is a density against which I can run a Metropolis-Hastings algorithm. That's the point. Okay, that was it for the Brownian case. So when my target diffusion had a diffusion coefficient which was 1, or at least known well enough that I can apply a Lamberti transform to make it 1. What about the Wright-Fisher diffusion, which is certainly not such a diffusion process? In one dimension, I can apply a Lamberti transform to the Wright-Fisher diffusion, but it will turn out to have a drift coefficient which is badly enough behaved that that previous algorithm kind of goes out the window. You can write it down, you can even run it, but the acceptance probability is going to be horrible and you're going to be simulating for the rest of your life. So it's not a good idea to try to do that directly. It's much better idea to identify a different process that you can simulate from, not a Brownian bridge, but something else which more closely resembles the dynamics of the Wright-Fisher model, and in particular has boundary behavior which is similar. So if I only had one boundary, then a Bessel bridge would be a natural candidate. That's what would be the first thing to try. The Wright-Fisher diffusion also has a second boundary, and it'll turn out that actually a particular Wright-Fisher diffusion is kind of the easiest case to start with. So suppose I'm interested in this diffusion here at the top. This is a Wright-Fisher diffusion with weak genic selection and mutation in both directions. Yeah, that does not resemble the sort of diffusions I was talking about in the first half of this talk. However, it has a particular kind of transition density expansion in the neutral case. So this thing over here is the transition, is the density of the Wright-Fisher bridge from x to y in time delta. I'm looking at some intermediate time t in the middle, so t is between 0 and delta. And this is just the dummy variable describing the states, and these are the three parameters. So I'm looking at sigma equals 0, which is the neutral case, and the mutation rates are still general. I can expand this thing into a horrible mess. This thing over here is a beta density. That's all we need to know about it. And these things will turn out to be a four-dimensional probability mass function. They can be represented as this sort of mixture of binomials, beta densities, a beta binomial PMF, as well as coefficients which are themselves only expressible via infinite series. So this is a sort of unpleasant quantity to look at, but the important thing is that it's a probability mass function on these four subscripts. And so if I just had this first term over here and these four sums on it, it would sum to 1. And so this thing in general is a mixture distribution. And so a conceptual way to sample from this Wright-Fisher bridge, and remember sampling from bridge densities was the key thing I needed to be able to do in order to make my exact algorithm work. That's why I'm talking about this bridge density. A conceptual mechanism for sampling from this is to generate these four indices M, K, L, J from this distribution, and then generate a realization from the corresponding beta distribution, and that's it. If I could do that, then I have a realization from my Wright-Fisher bridge in the neutral case.
I'm a bit lost. What are these M, K, L, J exactly?
They are dummy variables which I happen to need in order to get unbiased draws from this density. So this is just a series expansion of this bridge density.
They don't have like a specific meaning.
No. Yeah, do they? I don't think so.
You can interpret it as lineages, right?
Yeah, so if once we get down to this QM, this will sort of be the number of lineages remaining in an ancestral process. For the purposes of my talk, that's somewhat coincidental. But yeah, you can sort of interpret this a bit like running ancestral processes backward in time from the end point of your bridge and simultaneously forward in time from the start point of your bridge, and you're looking at how many lineages remain in each direction or something to that effect. Okay, yeah, so this part's easy. I know, even I know how to sample from beta densities. I don't know how to sample from this thing. It's expressed in this sort of form. And these coefficients, again, in the sort of top line, are relatively straightforward. If I can get M and K out from these two coefficients, then these are densities that I know how to handle. And so actually, it's enough for me to tell you how to sample from this fraction. This is one of these QM coefficients, a different QM coefficient, and a normalizing thing on the bottom, which is again just a transition density of a Wright-Fisher diffusion. And the issue, of course, is that these QKs are themselves only known as an infinite series. And so I need to tell you how to sample from a probability whose mass function can only be evaluated in the form of an infinite series. That can also be done. I've kind of reformulated this a bit more nicely here. But I think I've said all of this already. So this is where I want to go next. Suppose I have a probability mass function, P of M, which is unavailable, but I have two envelopes, L and U, and they are sort of sub-probabilities and super-probabilities, if you like, on these P's, in the sense that if I form cumulative distribution functions using these L's and these U's, then this T will always be underneath the CDF of P, and this T plus will always be above the CDF of P. And as K goes to infinity, they converge to exactly the right thing. And crucially, these things I'm assuming are tractable. So I have an envelope of approximations for all of my probabilities individually from above and from below.
Yeah.
Now, what can I do? Well, I'm sort of pretending to use something very, very simple here, which is conceptually just a kind of inverse CDF method. So you may know, if you've ever run into any kind of simulation course before, that if I want to simulate from a tractable one-dimensional distribution, then what I can do is simulate a uniform random variable, plug it into the inverse of my target CDF, and the corresponding evaluation has the right target distribution. And so I'll be doing that, except I have to use these approximating versions, and I have to refine them enough to get the correct outcome. And that's what's expressed in this algorithm over here. I start from a candidate, so this is just the least possible realization of my variable. This will be the level of my approximation, and here I'm simulating that uniform random variable that I already indicated I was going to need. Then, while my uniform is in between my two approximating envelopes, I just increment my level of approximation. And now, what happens once this condition is violated? Well, either my U is below the lower envelope, or it's higher than the upper envelope. If it's below my lower envelope, then, well, actually, I'm done. I know this is the first instance where my lower envelope has been high enough that it's now exceeded the U. Any inverse CDF method using the correct CDF would have terminated by now. And so I'm also well within my rights to terminate this method and return the current instance of my variable m. Conversely, if it's the other case where U is above this higher envelope, well, then I have to keep going, because when I add to my refinement or add more variables, the upper envelope could still grow, and so it could still get back above the level where I am now. And so all I do is I increment m, and I start looking at incrementing my approximation again. This sort of method is already in De Broy's book from the 80s, where he introduces it as an alternating series method. He assumes that this P is available as an alternating series, and uses the kind of odd entries for one of these and even entries for another thing. But this slightly more general formulation in terms of general upper and lower approximating envelopes is exactly identical. Using this for the Wright-Fisher diffusion turns out to be slightly more complicated than what I have space for on the slide. If you want to know the details, then I suggest you ask Jere, who knows them considerably better than I do. But anyway, I have access to this method, so you'll believe me that I am able to simulate from probability mass functions defined by infinite series expansions, and that's exactly what this Qm is. And actually this P in the denominator turns out to have a similar sort of infinite series expansion, so I have another Q coefficient here, and then I just have binomial terms and beta terms. And so in order to sample from this ratio, what do I have to do? Well, I haven't written it down, but I have an approximating upper and lower envelope for a Q. For an individual Q, I can write down these T minus and T plus things on my simulation slide. And then if I use the upper envelope on the two Q's in the numerator and the lower envelope on the Q's here in the definition of this transition density in the denominator, then I get a convergent upper envelope for the whole fraction. And vice versa. If I use lower envelopes in the numerator and an upper envelope for this guy in the denominator, then I get a lower bound for my whole ratio. And so, in fact, that kind of single Q case, if you will, is enough to also handle this fraction exactly. I can draw samples mk from this sort of fraction. Once I can do that, I can then simulate realizations from this binomial. And once I've done that, I have enough information to get a realization from this beta density. And once I've done that, I have enough to get this beta binomial. And I can get realizations of the exact probability mass function for this PM KLJ on the previous slide. So in principle, I know how to get samples from this using finite computation. And I have, again, to emphasize, this is only for the neutral case. My particularly want to be able to handle the non-neutral case because, well, natural selection is often quite difficult to formulate in backward time coalescent process type models, and it's very nice to be able to use the forward in time model for selection in particular, and so it's of particular interest to be able to handle this. But now I know how to get exact draws from bridges of neutral Wright-Fisher diffusions. Okay, so now I start playing that game with the Radon-Nikodym derivative. So my neutral Wright-Fisher proposals are going to be playing the role of the Brownian bridge in that initial algorithm that I showed you. And I'm going to write down the Radon-Nikodym derivative between this thing with sigma equals 0 and this thing with sigma positive, and hoping that I can express that as a rejection probability again. As long as I can do that, then the same sort of argument follows through, and I can use a Poisson process in order to generate realizations of my accept-reject step without ever needing to evaluate an infinite dimensional quantity. Here we are. What does a non-neutral bridge look like? Well, the law of a non-neutral bridge can be expressed as the Radon-Nikodym derivative between a non-neutral process and a neutral process. This Radon-Nikodym derivative has a very familiar form. I have a transition density of the non-neutral Wright-Fisher diffusion and the transition density of the neutral guy. Then I have an exponential. There's one of these capital F functions, but these only depend on the endpoint. And then there's this same phi function again. Of course, I've had to specialize the phi function to my particular form of drift. But either way, the same sort of form falls out. The only things in here which depend on the path and not just on the endpoints is this guy. It does turn out to be bounded below in the Wright-Fisher case, so I can form my phi minus, and this thing again is less than or equal to 1, so I can interpret it as a probability, and in particular a probability that an inhomogeneous Poisson process has no points under the graph of my diffusion path. Here I've just written down for reference what these functions turn out to be. Phi, you can see, is just a polynomial, and so clearly it is upper bounded and lower bounded nicely. And actually the fact that we get such a nice upper bound is a consequence of the fact that the neutral Wright-Fisher diffusion is a particularly well-chosen proposal distribution for the non-neutral Wright-Fisher diffusion. And this F also has a very, very simple form, which only depends on really the selection coefficient. Okay, so here's the Gibbs sampler for the Wright-Fisher diffusion. Gibbs sampler for the Wright-Fisher diffusion, and this slide is sort of noisy, but actually this is exactly the same as the same slide for the Wright-Fisher diffusion. The only thing I've really changed, these are all exactly the same, except I've said this is now the Wright-Fisher exact algorithm rather than the Brownian exact algorithm. And over here, I previously had the distribution of increments from a Brownian motion, so the Gaussian distribution. Now it's the distribution of an increment from a neutral Wright-Fisher model. But again, everything over here is tractable, is something that I can write down on a computer, except for this guy. I don't know a closed form for the transition density of the Wright-Fisher diffusion, but it has that same series expansion that we saw already, and I've covered how to handle that. So you can kind of generate accept-reject decisions against this sort of a target density, even though you don't know how to evaluate this exactly in closed form by using that same sort of approximating series trick that we used previously for the Q functions. A word of caution here on the bottom. It is essential that you write this density, this target distribution, against a dominating measure which does not depend on any of the parameters. That's kind of, dominating measures are something which people in statistics and in computational statistics tend to very readily ignore because we're used to simulate sampling from densities defined on RD. Well, you just have the Lebesgue measure and everything's dominated nicely. In the diffusion setting, that's no longer the case, and it's very easy to lose track of what dominating measure you're working with. And if it turns out that your dominating measure has a dependence on one of the static parameters, for instance, well, then when you're iterating your algorithm, you're changing your dominating measure at each step of the algorithm, and it's no longer clear whether your output has any meaning. Again, if you sort of want more detail on this, then I suggest you ask Jere. It's probably best you wait until I walk out the room first, though, if you want any kind of honest answers. Okay, I have, what, about 5 minutes left, so let me give you a quick kind of overview of what are some easier approximate things you can do if you don't want to bother going through all of that. So, suppose I have a diffusion model. And now I've written down a more general one where I actually have a variable diffusion coefficient, and it's even allowed to depend on the parameter. And the reason I'm able to do that in such a cavalier fashion is because the first thing I'm going to do is junk this model. I'm not going to use it. I'm instead going to say it's good enough for me if I have this sort of approximate discrete time jump skeleton of my diffusion. I fix some small time increment delta, and I say, well, xt plus delta is defined by the Euler-Maruyama scheme corresponding to this diffusion. And the law of this guy I know. This is just the Gaussian increments iterated. And so I can very easily write down a target distribution which is approximately correct, but has some bias which is quite difficult to quantify in any generality. But yeah, this right-hand side is completely explicit, easy to evaluate. And for a diffusion like the Wright-Fisher diffusion, this is a bit problematic because, of course, these Gaussian increments have no obligation to behave well around boundary conditions. So this diffusion feels quite free to escape the unit interval. If it happens to be at a state which is close to a boundary, the Gaussian increment will happily take you to an allele frequency greater than 1. And that's something you have to deal with to modify this scheme a little bit. But that has been done for the Wright-Fisher diffusion. There's a very pleasant paper by Dangerfield and co-authors where they show you how to modify these kinds of schemes to take into account boundary behavior. And you can still write down densities. Here you can then pretty much just apply standard Metropolis-Hastings algorithms, for instance. So this is the corresponding Metropolis algorithm. I initialize my state from some static parameters and realizations of my diffusion at my discrete time points. And then what do I do? Well, I sample a perturbation of both of these guys' parameters and diffusion models from a proposal distribution, and I do my Metropolis-Hastings accept reject. It's somewhat messy to write down all the variables involved, but conceptually there's nothing hard going on in there. It's just a ratio of proposal densities and a ratio of the target densities, and I accept or I reject in the way which has become familiar thus far. There is a Wright-Fisher algorithm implemented along these lines, which has its time discretization in a slightly more implicit way, but ultimately they kind of, the algorithm is still in the style of this thing, even though they do something which is a bit closer to exact simulation, but not quite. There's still a time discretization lurking behind if you actually look at the paper. The big advantage of this method is, well, there's two really. The first one is this guy. It's much easier to handle a much broader class of models in this sort of way. And in particular, if you think of the Wright-Fisher diffusion, I said earlier on that the cost of this sort of exact sampling algorithm depends on how closely you can make your proposal bridge density resemble your target bridge density. If those two are very, very similar in the sense that the Radon-Nikodym derivative is almost 1, then you will very rapidly accept proposals and you don't have to iterate your proposal algorithm many times. Your computation is going to be fast. Conversely, if they're fairly different, then you're going to generate lots of Poisson points with high probability. One of them is going to fall under the graph of your diffusion path. You have to throw out the whole path and start again, and so you waste a lot of time. That becomes a problem if your selection coefficient is large. And so really this sort of thing in practice is only applicable to selection coefficients in this diffusion of, let's say, order up to 10 or 20. Is that about a fair number? yeah, well, if you get bigger than that, you're going to be simulating forever. Whereas this Euler-Maruyama scheme, well, it still just works. There's no kind of complicated business involving what the magnitude of the diffusion coefficient is or anything. You're simulating a slightly approximate model, but an explicit one. So there's no mismatch between proposal and target or anything like that, and so there's no increase in cost when the selection coefficient gets large. On the other hand, it is worth keeping in mind that this is the Wright-Fisher model with this kind of selection is supposed to be a model of weak selection. So if your selection coefficient sigma starts becoming big enough that it sort of approaches, well, I'll write this down rather than say it in words. It's supposed to be based on this kind of rescaling of S, which is a per generation selection coefficient, and N, which is the effective population size, and that's supposed to be fixed. Now, if sigma gets too large, then it's no longer necessarily plausible that S is of the order 1 on N. And so you probably shouldn't be using the Wright-Fisher diffusion with selection model for very large selection coefficients anyway. So it's unknown whether this problem happens to nicely coincide with the computational limits of the algorithm. I think it would be quite amazing if that were the case. And so this isn't the kind of get out of jail free card by any means. You still need to be careful when applying the algorithm. But yeah, if you have large selection coefficients, then you have to do something like this, but you also should think carefully about whether you should be using this model at all. There is also a way in which you can make progress using series expansions of transition densities. That's been done for the Wright-Fisher model with selection by Jun Song and Matthias Steinrücken. I'm out of time, so I won't go in through those details. If you're interested, this is going to be up on the repository. Thank you for your attention.